next presentation is from Tom Arney about ice-rafted feldspar grains in recent shelf sediments from West Antarctica, the provenance pathways from lead-isotope compositions.
Yeah, it's quite a long title, but it'll be about using lead isotopes from West Antarctica for past ice sheet extent. So ice sheet extent is a very important factor for global sea level. Most of you in this session probably know this graph, but just in case, this is from the latest IPCC report, and it shows sea level rise observations on the left, and then projections on the right up to 2150, where most scenarios project a rise between about 0.5 metre and 1.5 metres. But up to 5 metres of sea level rise cannot be ruled out due to deep uncertainty in ice sheet processes. So that's what we hope this work will help us provide a tool which can reduce those uncertainties, or help to, by reconstructing past ice sheet extent. Yeah, so the modern Antarctic ice sheet covered almost all the Antarctic continent. That's the thin white line around the outside. But in the Pliocene and some very warm Pleistocene interglacials, the ice extent has been modelled to be significantly smaller in the West Antarctic interior, particularly in the Amundsen Sea and Ross Sea areas. We can test these models' assumptions and the physics behind them by confirming the paleo extent of the ice. And that should help improve the models and therefore also the projections. So one way to improve, to reconstruct the paleo ice extent is by tracing the provenance of glaciogenic debris. So as an ice sheet flows, it erodes material from its base, particularly towards the downstream areas, and that debris is incorporated into the bottom of the ice sheet, and then when it reaches the ocean, it melts out of the ice shelf or iceberg and accumulates in marine sediments. And the provenance of that IRD can then give us a clue about where the ice was eroding from, and therefore where it was to extend to the ice sheet. IRD includes everything from mud to boulders, but I have analysed the sand fraction to constrain the transport just to icebergs. And the more provenance proxies we use, the better. The picture of the where the ice was sourcing the detritus. So here we've applied the lead in feldspar proxy to West Antarctica for the first time. So there is lead in feldspar data from West Antarctica, but it's mostly being used for igneous petrology and continental reconstructions. And it's almost all onshore bulk data, like on the map there. And the bulk data means that it's all from one rock and analysed in solution mode, multiple grains. And so there's an averaging effect on that. And partly because of that, there's this homogenous data distribution. In the centre of this lead plot, there is a slight, a darker ellipse behind it. I'm not sure if you can see it here. But in the North Atlantic and in East Antarctica, individual grains of ice-rafted feldspars show much more variance and have proved useful for provenance. So we've applied this to West Antarctica. 600 individual grains, more than, from 24 marine sediment core tops from the continental shelf, fired a laser at them. So each data point you see in this is one sand grain. And here are the results. So this is a cross plot of 207 normalized lead, and we've replicated the central cluster from the bulk data, but it's not homogeneous. The distribution is not all the same. There's definite denser bits and less dense parts, and you can also find these clusters away from the main body down here in the bottom left, the less radiogenic part of the plot. So I fitted a 6-component Gaussian mixture model to this data, and we've got 5 distinct clusters, 3 in the central area, the red, dark blue and light blue, and then 2 yellow and green down to the bottom left. Importantly, the clusters are not just coincidentally clusters in lead-lead plots. They are also geographically restricted to regions within West Antarctica. So this is quite a busy map of West Antarctica, I apologise, but the Pacific Ocean at the top in grey, the West Antarctic Ice Sheet in white and blue at the bottom. The blue is the flow speed. And then each core site has a pie chart. Diameter is the number of grains we analysed, and the sectors show the percent of the grains which fall within the clusters with the corresponding colours, same as the scatter up at the top right again. So the red and pink seem to be present pretty much across the region, so aren't particularly helpful for provenance, but the dark blue seems to be concentrated in the Amundsen Sea embayment, and particularly in the east around the Thurston Island block, coastal block. Light blue down here seems to be present mostly in the Bellingshausen Sea. And then the other two are even more restricted. The yellow has only 8 grains, but they're all from just one core, just off the Sulzberger ice shelf on the left there. And the green is particularly important because it's only present in these 2 cores, one in the eastern edge of the Ross ice shelf, and the other at the outlet of Thwaites Glacier, where it's a very strong signal, actually, about half the grains. So we propose that this is a new indicator of Thwaites derived debris, if you observe it in the Amundsen Sea, the wider Amundsen Sea. Although we don't know the upstream source of this material, or whether the 2 sites are getting the same debris. So this is a zoomed map of the previous one, and you can see that the green grains from Thwaites Glacier are not observed in more distal cores out across the continental shelf. So we think there's an offshore dilution effect, mostly from the Thurston Island inputs that's swamping the Thwaites signal. If erosion at Thwaites bed changed significantly, you could expect a change in the proportion of these green grains, either due to Thwaites Glacier advancing during glacials, or even the disintegration of its basin during interglacials. So we think this is possible proxy for Thwaites Glacier dynamics based on this anomalous lead, less radiogenic cluster of lead isotopes. So to conclude, lead isotopes in feldspars can be used to distinguish different West Antarctic IRD sources. We found 5 distinct clusters in lead isotopes, 4 of which are geographically restricted and useful for provenance, and 1 of which is restricted almost entirely to Thwaites Glacier, which we propose as a new proxy for Thwaites dynamics. So future work, we're working to confirm and characterize these clusters with other geochemical systems, including dating the same grains with the new in situ rubidium-strontium mass shift laser ablation method, which should give us some clues to tie the clusters back to real sources. And then in a sister paper, we're also investigating glacial interglacial variability of these clusters. So there's a QR code if you want more information or contact information. And finally, I'd just like to say thank you to these institutions for support, funding, and or samples. Thank you.
With questions for Tom, we have immediately.
Yeah, just about the sampling method. Did you always choose the same depth, or did you use several depths across the?
It's everyone wants core tops, so we've had to be we've been. I think the maximum we ever went to was 10 centimeters below seabed, but most of them are sort of up to 5 centimeters. But we don't have to adapt to if we got to a core that was already heavily sampled, we just had to take what we could.
Do you expect an error due to coring, top loss or
disturbance? Yeah, it's possible. Yeah, and a lot of these cores don't have real age models. We assume that the core top is recent. We hope it reflects what's currently being taken off. Yeah, exactly. Yeah.
All right, thanks.
There's another question here at the back.
Hi there, thanks for a great talk. Just curious, what motivated you to analyse to 207 instead of the conventional 204?
Yeah, the laser ablation method means that the 204 sensitivity isn't that high. And I don't actually need 204 for this because I can just normalize to 207, use the other two isotope ratios, which means that the errors are then smaller. And in fact, if I can go back, this might not work. So the errors here are, a lot of them are smaller than the markers, and it means that the clustering is a bit more reliable because, as far as I know, there's not a useful and easy way of clustering involving the errors as well.
Sure, it might be a useful exercise if you have some larger grains to try a larger spot size to boost the signal and just see if you pull out the same clusters.
I'm already using 150 microns, which is as big as our laser can go. So yeah.
Be interesting to talk to you about that after.
Yeah, please.
Okay, thank you, Tom.
Sure.